to see my presentation. If there are any technical issues, yeah, please let me know. Yeah, don't hesitate to interrupt me. Okay, cool. So yeah, first of all, I'd like to thank the organizers for giving me the opportunity to give this talk at the Qiskit Fall Fest. So my name is Alexia Salavrakos, and I'm a researcher at Quandela, and I'm going to tell you about the full stack photonic quantum computing that we're doing at Quandela. So our company was initially a spin-off from an academic group, the academic group of Pascal Senlar at C2N. It was founded in 2017, and it has grown a lot since then. So today we have about 100 people, even more, with many scientists and engineers, and focusing a lot on research with scientific publications and patents. And our main offices are just in the south of Paris, in Massy-Palaiseau, but we also have a few people working from countries in different parts of the world, including, for example, we have a recent office that opened in Canada. So I wanted to highlight first, when we talk about photonic quantum computing, there are kind of two big paradigms. There is the discrete variable or the continuous variable one. So I'm not going to tell you about anything that is continuous variable. So that would be, for example, what Xanadu is doing. And that's not what we're doing at Quandela. We're working with discrete variable photonic quantum computing. So that's what I'm going to focus on. Why did I call this presentation full stack? It's because we are doing a lot of different things. So initially, Quandela was a hardware company, and this is still, I would say, something that's like very strong and at the heart of the company. So we are really building quantum hardware. We have some quantum processing units, QPUs, that are available today. And we also have a roadmap for a fault-tolerant quantum computer. But we also do a lot of software. So we have a simulation that's tailored to our devices. We have a cloud platform to interface with our QPUs, etc. And on top of the hardware and software, we also have some teams that are working a lot on looking and developing applications, also algorithms, see a bit what can be actually run on our platforms today and also in the future. So the structure of the talk reflects a little bit this full stack aspect. So I will tell you first about the experimental setup and also what software tools we have. Then I'm going to do a zoom in on linear optical quantum computing. And then I'm going to tell you some examples of algorithms that we have developed. And at the end, I will tell you a bit more about our plans for the future, our roadmap, what is next, basically. So yeah, let's start with the experimental setup and the software stack. So this is like what our near-term quantum processors look like the ones that, for example, you can see here an article that we presented a couple of years ago. It was for the QPU called Ascala. And really at the heart, at the beginning of the setup, what is necessary is to have a good single photon source. So the object that is going to generate the photons that we will use to do the computation on. So we have the following desired properties for a single photon source. So here we can imagine with a drawing the source is here, and here are the photons that it's producing. So the first important thing is that we would like to have single photon purity. So we want, whenever we activate the source, we want it to produce always one photon at a time. So we don't want to produce, for example, 3 photons at a time, sometimes 2, etc. We always want 1. We also want our source to be kind of on demand, to have high brightness. So every time that we activate the source, we would like there to be a photon emitted. So here the absence of photon would be a lack of on-demand property. We would also like our photons to be indistinguishable. So we would like them to have the same properties. So here I use the color blue and red to show that the photons are a bit different. They could have a different frequency envelope or something like that. So ideally, we would like them to be similar, to be exactly the same. So this would be an ideal photon source. We are activating it in some sense, for example, with a laser, and it's producing always single photons that are indistinguishable. So at Quandela, actually, this is how the company started. We are able to create single photon source from quantum dots. Quantum dots are these sort of artificial atoms that you can build in semiconductor material, so in this gallium arsenide, and you end up with like these different energy states that are very well defined in space. So here. And if you shine a laser onto the quantum dot, you can excite it to a higher energy state. And then deterministically, it's going to go back to the initial energy. And in the process, it's going to emit a photon. So that's, let's say, basically how we activate the source. We're like shining a laser on it. And we know that it's going to deterministically have to emit a photon. Of course, it's not clear like in which direction this photon is going to be emitted, right? It could be emitted kind of in any direction. And so for this reason, we place our quantum dots in so-called micropillar cavities. You could imagine like this micropillar cavity as like being like a lot of somehow mirrors all together that are allowing to redirect the photon in a specific direction. And then from there, you can have a fiber that collects the photon and you can use it for the rest of your setup. So we have arrived here at this point, right? Like the photon has been collected and it goes to the rest of the setup. So here this filtering is like removing somehow the light from the laser, and then it goes into what we call a demultiplexer. So this is simply a device that allows to transform like a train of photons into photons that can be arriving at the same time in different modes. So, you know, you would have like, for example, here, 6 photons that arrive together in the demultiplexer, and you are able to prepare states, you know, that are going to be here as 6 photons together entering the chip. So this is done simply like with time delays, basically. But it does require quite a bit of engineering. Then after that, the photons are ready to enter the chip. So this is where we're doing like all of the somehow gates, so as you can imagine, like quantum gates or like operations that we do on our photonic states. And it's very cool that today we're able to use chips, because I would say before, like most of the optical or like photonic experiments, they were happening like in these big setups in free space. And of course, this is not exactly scalable. So it's much nicer to be able to implement all of that on chip. Then after the chip, the photonic states are being sent to these superconducting nanowire single photon detectors. So it's also like this superconducting material that reacts in a certain way to the arrival of a photon. And it has like, I think, very good efficiency for the detection. The only thing is that current technology is much more oriented towards threshold detectors. So it just indicates if there is a click or no click, but it doesn't tell you exactly like how many photons were in each mode. So this would be like photon number resolution detectors that are still a bit difficult somehow to build. So, okay, we've arrived kind of to the end of the setup. So now that we have like these results of these detections, basically we have kind of finished somehow our computation. And something that I wanted to say about the noise. So, you know, at the beginning, I was telling you in the source, it's important to have a source of pure single photons. It's also important for photons to be indistinguishable. So those would be like kind of noises that appear from the source. But there is also a type of noise that is happening kind of all over the setup, and that's photon loss, of course. So as you know, it's something, yeah, kind of major in photonics. It affects the whole circuit. So here in this plot, you can see for the Ascala QPU that we had presented a couple of years ago, you can see the values of the efficiency. So that's like basically 1 minus the loss for all of the different components, the chip, the detectors, etc. And you can see that overall it's just 8%. So that's actually a very good number, I would say, for the industry, but it's still like quite, yeah, as you can imagine, like quite a major challenge. And another important point is that the scaling of the loss is exponential with the number of photons in an experiment. So of course, if you are sending together, for example, 6 photons into the chip, or like generally like all over the setup, you're going to have the probability that all of 6 of them make it to the end. It's going to be 1 minus the efficiency to the power of 6. So yeah. Sorry, 1 minus the loss to the power of 6. So yeah, it's becoming quite harder as you increase the number of photons. Okay, so yeah, that's kind of like so far like all of the hardware part that is necessary. But of course, to be able to interact with our processors and to be able to, for example, collect and like apply some post-processing on, etc., from the outputs, we need some software. And so here comes in Perceval and also our cloud. So Perceval is our software platform for discrete variable photonic quantum computing. It's like mostly written as a Python package, but there's also like some compilation tools and backends that are going on underneath also in other programming languages. So if you want to have a look at it, to use it, there is a website with a lot of documentation, and you can just install it with pip, for example. And it's giving us the interface to access our QPUs, as I was saying. So you, as a user, you would write down your program in Perceval, which contains maybe some input state, some circuit that you want to do. It's sent to the clouds, then goes to be like compiled into the exact values of the optical components that are being used in the lab. And then it happens on the QPU, and then Perceval returns you the coincidence counts and the single photon counts. So that's, I would say, for now, our main tool. But we also have launched recently another very important software tool called Merlin. And it has more to do, I would say, with the machine learning, with the algorithm design, exploration. It's kind of focused on photonics, but it also allows for other kinds of platforms. And there is, for example, compatibility with PyTorch and with these sorts of APIs. And it's really, whereas I would say Perceval is really the tool that you would want to use if you want to simulate like a small experiment, see exactly what's happening, add noise, all of this stuff. And also, yeah, directly like, I don't know, maybe send your small experiment to the QPU. If you want to do more like testing, exploration of QML models, all of that, then it's more Merlin that you have to go to. So at the moment, we have quite a strong initiative going on with Merlin about reproducing papers from the literature on the Merlin platform. That's also something that you can take a look at if you're interested. And yeah, if you want to train some hybrid models, it's really going to be much faster in Merlin than in Perceval. So I would say the two tools are quite complementary in that sense. So yeah, let me know if there are any questions so far, and otherwise I go to kind of the next chapter of the talk. So yes, yeah, if there are no questions, then yeah, we go on to the zoom in onto linear optical quantum computing. So here I would say, like, you know, when you talk about generally like photonic quantum computing, it can mean like different ways to use photons, different setups. But in the near term, what makes the most sense and what is really like the most practical is to use linear optics, like to use a linear optical paradigm. So this is what we're doing in our setups. We're doing linear optics. What do we mean by linear optics? What's the exact definition? Well, it's basically you're using beam splitters and phase shifters on an input of single photons in order to perform quantum computing. So you would have your photon source, you would have your detectors, and you are preparing some so-called Fock states. So the Fock states, if you have M modes, so that could be like, for example, M physical modes on your chip, but that could be also something else if you're considering like time encoding or polarization. And you're looking at the number of photons that are in every mode. So here you see that we have prepared the state 1, 0, 1, 0, 1, 1, because you have one photon in the first mode, one in the third mode, one in the fifth, and one in the sixth. So then there is this evolution happening here with the beam splitters and phase shifters, and you then observe at the end another output Fock state where you could have, for example, also collision cases. So you can have several photons that are going into one mode. For example, here, 1, 2, 0, 1, 1. So these Fock states are quite important to describe really what's going on in the linear optical setup. So yeah, if we want to look at beam splitters and phase shifters in terms of the matrices like that they represent. So we have beam splitters that are U2 transformations that are happening on like two modes, and phase shifters are U1 transformation just happening on one mode, and they both look like this. And then we have a really cool result by Rek et al., which is that for any unitary UM, there exists an M-mode linear optical circuit that can implement it. And we know, like we have a description in terms of like all of the beam splitters and phase shifters that you need to somehow align and which values to give to the different phases in order to implement that UM. So this is the first result, which was from Rek, the earlier result, Rek et al. And then there was also another way of decomposing unitaries that was developed by Clements and co-authors. So you can see like the two setups, they're equivalent, but the second one is kind of more short. So it's kind of often considered more practical because it allows for like less loss in a sense, because the photons have to go through like a shorter circuit. So something very interesting is that this whole setup of linear optics, it corresponds to the scenario of boson sampling that you might have heard about before. So it was proposed by Aronson and Arkhipov in 2011, and it's exactly what I was describing to you. And like it's important to note that the probability of measuring a specific output Fock state is related to the permanence of a submatrix of the matrix U here, of the unitary. So the permanent of a matrix is like the determinant, but with plus signs everywhere. And unlike the determinant, it's actually quite hard to compute classically. It's quite costly. So, like given this information, Aronson and Arkhipov designed the boson sampling task, which is to sample from the output probability distribution of a discrete variable linear optical circuit. So more specifically, you have to sample these outputs with this PS that is proportional to a permanent. And so this is kind of hard to do classically, conditioned on some widely believed complexity theory conjectures. And this allowed Aronson and Arkhipov to define thus a task which can be a near-term demonstration of quantum advantage. So I would say that this is something that a lot of people that are working on photonics and on linear optics are like generally working towards being able to do demonstrations of boson sampling. But something which is also a challenge is that this task is not necessarily useful. I think like actually like a lot of tasks that are associated with quantum advantages or demonstrations of quantum supremacy and this sort of stuff, it's not always associated with a use case. So it's also a big challenge to try to find interesting use cases related to boson sampling. Yes, so that's the original article, and this is like in the continuous variable framework, you can define an equivalent of boson sampling called Gaussian boson sampling. So, okay, you might be thinking, okay, so far, where are the qubits? Where are the gates? Where is my like Pauli gates? Where are my CZs and so on? If you're familiar with the more like the usual way of thinking about quantum computing. Well, it turns out that it's also possible to define qubits and logical gates, of course, with linear optics. So for that, you need to choose an encoding. One option is to choose the dual rail encoding. So it means that for each qubit, you need to use two optical modes. And you say, for example, that if the photon is in the first mode, I have qubit 0. And if the photon is the second mode, I have qubit 1. So here you have the qubit state and here the Fock state. And in that framework, well, I mean, I gave the example with like the physical modes, but we can also choose other encodings like polarization if you want. And in that framework, it's quite easy to do one qubit gates. Like, for example, okay, here I didn't normalize the state, but like if you wanted to apply like a Hadamard gate or something like that, you could do it quite easily with just a beam splitter. However, there is the challenge that some two qubit gates cannot be achieved deterministically with just passive linear optics, so with just the elements that I described so far. So you have some options still to do these gates. For example, you can use some nonlinearities which come from materials which are unfortunately quite hard to obtain and to use in your setup. You can use post-selection or heralding, or you can also use feed-forward, which was used, for example, in some proposals for like scalable linear optical quantum computers. So that would be like maybe something that's more for the future. But at the moment, we can use quite easily post-selection or heralding. So here is the example by Ralph et al. Of a CNOT gates that you can do with post-selection. So here with modes 1 and 2, you have qubit 1, modes 3 and 4, you have qubit 2. And you need to add like 2 extra modes and do some post-selection in order for your CNOT to succeed. So it's kind of not super easy, like requires some cost to define. So this also then has an impact on how you would design algorithms on linear optics. So I would say that there are kind of two approaches. I would say the first one is the one that's maybe more straightforward. It's the one that's like qubit or circuit based, where you use the kind of encoding that I just described, like with dual rate encoding. You do your CNOTs maybe with post selection or with something else, and well, CNOTs, you do your other gates and so on. And maybe it's possible that your circuit, especially if it has 2 qubit gates, is going to require like some post selection and is not going to always work with like 100% probability. So like you would be able to keep only a certain amount of your runs. So that's kind of a nice approach because there are lots of algorithms that are already designed in this like qubit based approach. So it's quite attractive because you can just translate results that exist from the literature. But it's also interesting to look at the somehow what we call the photon native or photonic native approach. So in that one, you don't have to think about stuff like post-selection or heralding and all of that. You're just looking at evolution happening only in like linear optics, so your unitaries that are evolving input Fock states to output Fock states. And so at Quandela, we have several examples of algorithms that we've designed like within the two paradigms. So for instance, we had a nice demonstration of a variational quantum algorithm solver for the H2 molecule using a qubit-based circuit. Then we also had, by my colleagues, this nice work on like clock encoding. So this qubit logic on qubits. So it's like a kind of a way to do a compilation using like qubits in order to do circuits like that with like a higher somehow probability of success in the post selection. So as you can see here in the plot, they were able to run the VQE for the LIH molecule much faster than if they had needed to use like the full just a simple qubit encoding. So there is also like some interesting compression techniques that you can use to avoid like the issues that come with post-selection. Then for some photon native examples, we developed like a nice variational quantum classifier that we demonstrated on our QPU, the Ascala one. So here the model is encoded like in the phases of the interferometer. There is also this very nice work from some of my colleagues for solving graph problems with the single photons and linear optics. So here, basically, the idea is to take the adjacency matrix of the graphs and somehow encode this adjacency matrix in the unitary that you have in your linear optical setup. And then you can, for example, check that some graphs are isomorphic by looking at the permanence of the adjacency matrices through the probabilities that you observe at the output of your experiment. We also did a fair bit of generative modeling, so using like these linear optical setups to generate data and see if we can train like models that are based on these chips. So we had like an article on a QGAN and also a QCBM where we also integrated some error mitigation techniques for photon loss in particular. Also, some of my colleagues worked on a photonic parameter shift rule. So you might be aware of what the parameter shift rule is. It's like this rule that allows you to compute gradients in quantum circuits, and that allows you to do like kind of big steps in gradient descent because you got like this exact rule. And they applied it also to like this generative model, and they could see that with the parameter shift rule, the photonic one, they could get convergence of the model quite faster. Also, some of my colleagues worked on doing reinforcement learning with linear optics. It was also very nice work. There is also some upcoming work coming on quantum convolution neural networks. So where basically QCNN is being defined in this time, not using only linear optics, but also using feed forward. So this component that allows you to do like adaptive operations given some measurements that you obtain on some of the modes. And so I wanted also to highlight that there is also another group that worked on QCNNs and other groups in general that are working on algorithms tailored to photonic devices. So, for example, you can see here names of like academic groups that are doing this sort of things. There was an interesting work on kernels from the group of Philip Walter, also more reinforcement learning using photonics, etc. So I would say it's quite an active area of research. We also had an interesting challenge that we did this year where we proposed to participants all over the world to try and classify mnist digits using linear optical circuits in a more hybrid pipeline. So there the idea was like that somehow the participants would explore not having like a fully, not necessarily a fully end-to-end quantum algorithm, but you could just put somehow the quantum algorithm somewhere like as a feature extractor and then have like some more traditional ML models working. So we have gathered all of the results from the participants in GitHub repository, and we wrote an article to summarize everything. And I would say like the spirit a bit of this Percival challenge joins kind of the Merlin platform that we have like recently developed. So it's, as I was telling you earlier, Merlin allows you to add like some linear optical and photonic models within machine learning pipelines. So it's like connected with PyTorch. You can just add, you know, like a quantum layer when you're defining like your neural network, and you just add a quantum layer using Merlin. So that's like, I think, quite handy. And the optimization is also going quite fast because you've got the backpropagation and automatic differentiation that can happen in the background. So yeah, there's also like some connections with cross platforms, being able to also go like gate-based to photonic and this sort of stuff. Okay, cool. So I see that I still have quite a bit of time actually for the roadmap and for what's next. But first, yeah, please interrupt me if you have any question on algorithms.
I think there's none, so.
Very good. Nice. So I can continue. Okay, so yeah. So this is, I would say, like all of the algos that I was showing you, it's like very stuff that can be like implemented on our QPU, stuff that is very tailored to linear optics and all of that, even if some of them are requiring some new elements like feed forward. But now we also have, of course, some teams that are more focused about the long-term vision. So how to build a fault-tolerant quantum computer. So in case some of you are not so familiar with the concept, so I wanted to recall the threshold theorem, which says that quantum computer with physical error rates below a certain threshold can, through the application of quantum error correction schemes, suppress the logical error rate to arbitrarily low levels. So that means that somehow if you can like have some physical error, so if you can remove enough physical error, have like components that have somehow high enough quality, high enough coherence, all of that, you are able to reach a point at which, or below which, if you're using quantum error correction, you can have computation that is as errorless as you want. So that means that quantum computers can be made fault tolerant. So it's quite powerful, although it's also, the threshold is usually quite like hard to achieve. So it's not something that we can reach like this year. It will require a few more years, but it means that once we've reached it with the appropriate error correcting codes, we can really do like somehow near perfect logical computations. So yeah, this was all of this theory and these definitions, etc., were kind of developed, I would say, like about 25 years ago, something like that. And for photonic platforms, a lot of the proposals for going towards fault tolerance, I would say, are based on measurement-based quantum computing. So I don't know if you've heard about measurement-based quantum computing before. It's also known as one-way quantum computer. And there, the idea is that you generate like these really like big resource states or cluster states, and you're doing like measurements on some parts of the state. And the measurements is actually you doing the computation. So you are also able to do some corrections on the qubits depending on the measurement result that you've obtained. But basically, you're sort of like starting with these huge states, making all the measurements, and that's how you do the computation. And it's equivalent to a usual like circuit-based model. And yeah, when I was saying a lot of photonic-based proposals are like related to MBQC, for example, PsiQuantum's roadmap is using fusion-based quantum computing, which integrates MBQC and fault tolerance, and which requires like the creation of like resource states and these so-called fusion measurements. And so on the one hand, we are also looking at how we could do something similar. And we have like some interesting paths with how, with our quantum dots, we can generate some interesting graph states that then can be used as resource states. So for example, we had a demonstration of how we are generating JJ states, which are like that, these multi-partite photon states, and which can then be used, for example, for resource states. But we also have another interesting way to generate entangled states from the source. So this was demonstrated in this paper from the group of Pascal Senna, our founder. And it's actually related to a proposal by Lindner and Rudolph on like generating like on-demand entangled photonic cluster states. So the idea is that you would apply like a magnetic field to your quantum dot so that it will have a spin that is can be in states up or down. And then once you excite that quantum dot, now that it has like this spin property, it will actually emit a photon that is in a different polarization depending on whether the spin was in the up or in the down state. So as you can see here, you can then generate like these sorts of states where you have entanglement between the spin of the quantum dot and the photon through the polarization of the photon. And then you can apply like spin gates in order to like change the state of the spin. You can rewrite it in this way, and then you can again excite it, and again it emits a photon, and so then you're going to have now entanglement between the spin, the first photon, and the second photon, and so on. And you could continue many times and have like these long linear cluster states. So this is quite handy, and like this is something that we could use to make also MBQC. But we also had like this sort of intuition and I would say very cool idea, especially from my colleague Paul, that you know, we can have these strategies like fusion-based quantum computing with many quantum dots. How about we use these quantum dots as the actual qubits, as the carriers of quantum information? So in that proposal, spin optical quantum computing architecture, we are using the spins of the quantum dots as qubits, and then we use the photons that are entangled with the spins in order to perform 2-qubit gates between different spins. So now you sort of don't have a fully photonic computer anymore, but you have like a sort of hybrid photonic and matter computer. So yeah, so again, the qubits are the quantum dots, and the photons that are entangled with the spins of the quantum dots are used to make gates between the qubits. So maybe it's a bit clearer if you look at this here. So you have like 2 spin qubits, they're emitting like these photonic qubits. Together they're entangled, and those are being rerouted to some small chips. And then there you can do on the chip like an operation, like for example, a CZ gate or something like that. You also have schemes for repeat until success so that you don't lose the information in case like part of the somehow, for example, if a photon was lost or something like that, you have like a protocol that you can follow. And this allows you to create, like to do, for example, a seeded gate between your two spins. And this is also very cool because if you imagine that you have your whole layout with all of the quantum dots, it means that you can do operations between quantum dots that are quite far from each other without having to, for example, go through other quantum dots, without having issues with connectivity, for example. So in the Spock paper, we looked at like the different effects of different noises, like distinguishability, the coherence of the spin, the failure of this Rust gate, and this repeat until success. And we also looked at the integration of a quantum error correcting code, the surface code, and we were able to obtain an area under which we know that we have a fault tolerant proposal. So we have thresholds for different errors, and under these thresholds, so in this area, we know that we can reach fault tolerance. So this is very cool because it also gives us like objective to work towards too, in terms of like the different errors needed to reach this threshold. And of course, my colleagues from the team that is working mostly on architecture are developing also more advanced version of this spin optical quantum computing architecture, different versions of Spock, for example, using here Floquet code instead of the surface code, etc. So I think I'm actually getting slowly to the end of the talk. So in terms of conclusions, like to sum up, so we have a proposal for full stack photonic quantum computing. So for the hardware in the near term, as you saw, we have some QPUs that are based on linear optics. And in the long term, we have this spin optical proposal. In terms of software, we have Perceval, that is a Python package with simulations that are very close to the hardware, where you can add noise, you can really see what's going on very precisely. And then we have Merlin, which has a more ML focus, which is allowing you to play around with PyTorch, adding like quantum layers in your machine learning pipeline, etc. And then, as I showed you, we have our team working also on algorithms and applications, doing like, as I showed, like VQE, classification, generative learning, etc. And for future directions, we are still in the applications and algo team, exploring use cases, trying to improve training of photonic circuits, improve compilation, these sorts of topics. We have also a team, device theory, who is working on topics like error mitigation, benchmarking, modeling of what's going on in the device. We have also software teams that are dedicated to the development of Perceval, Merlin, and there should be also some additional software that will come for like more mid and long-term scenarios. For example, for estimating resources that will be required in a Spock model. And of course, we have our scaling architecture team, and then also the experimental teams that are working together towards implementing Spock in the long term. And yeah, that's all I wanted to tell you today. So I see we still have quite a bit of time for questions. So in case there are any, go for it. Or if you want to send them to me directly through Discord, I would also be happy to answer in the chat. So thanks a lot.